voltage noise and or current noise. So most of the examples I'm going to do today are, I'm going to use voltage, but there are certainly current noises too. So for instance, if we look at this, this is a very old spec sheet for the 741 amplifier. It says SGS Thompson on it. And since they haven't existed for a while as SGS Thompson, they're now known as ST Microelectronics. This is an older spec sheet. Most of the newer spec sheets, the data sheets you get for the 741 operational amplifier, do not include any information about noise because for the most part, that's not a good choice these days for anything where you're in a noise critical application. So if you have, you've probably seen something like this before. The spec sheets have everything like the packages that it's available in, etc. The pinouts, of course, in a single op-amp version, that's pretty boring. Things like that. But if we jump ahead a few pages, maybe jump ahead one. It's not showing up very well, but that's the internal schematic. Roughly, you can see it's more bipolar design. You don't care too much about that. What we care about is the noise performance. So what do they tell us about the noise performance of the 741 operator? There we go. So really all we have is two graphs. They're versus frequency. If you can't read this, this is a log scale. We have an equivalent input noise versus frequency, and then we have input noise current, again, versus frequency. In one case, we go from 10 hertz to 100 kilohertz. In other case, we go from 100 hertz to 100 kilohertz again. So in one case, the units on the noise voltage are nanovolt per root hertz, and you can see that this is 5, 10, 15, 20, 25 nanovolt per root hertz. Little oddball units there. On the other side, the input noise current is mean square noise current. So that's amps squared per hertz. So for this data sheet, they did something a little odd. If you were going to display this in nanovolt per root hertz, or volts per root hertz, then you should really display this one in amp per root hertz. But they didn't. They displayed it in the square of the quantity. And so you get, this is the actual, what we call power spectral density, amp squared per hertz. As you can see, it tends to actually go up at lower frequencies. We will show today that that is not a big issue. You can also see one of the reasons why we like to maybe work with the square root of this number, not the number itself. So in other words, work with amp per root hertz rather than amp squared per hertz, because look at the units here. You can read that, 10 to the minus 23. So the floor here is about 10 to the minus 24 amp squared per hertz. Really small numbers. If we talked about that in terms of amp per root hertz, we take the square root of that, and at least it would be picoamps, 10 to the minus 12. So if that's bewildering, let's get down to work here and straighten some of these notions out a little bit. Okay? So if you don't know at all what that means, don't worry. We'll get you started on talking about noise. So just about anything you can think of including as simple as a resistor, has noise. But since we're talking about op amps, let's think about an op amp here, our 741. And just for the heck of it, let's connect it as a follower. So let's simply short the input back to the inverting terminal, and then let's ground the non-inverting input. So if we did that, and if we look at that signal with a noiseless oscilloscope, so suppose I had at my disposal a completely noiseless oscilloscope, so that the oscilloscope trace had no noise in it. If I looked at that oscilloscope trace, the output voltage versus time, I would see something that was on the average 0, but definitely had some fuzz there. Now, of course, when you look at just about anything with the oscilloscopes that we realistically have available to us, we're not only seeing the noise associated with this op amp, we're also seeing the noise associated with the oscilloscope itself. So pretend that that's not happening, and we're literally looking at the output. And so we have random noise here, so on the average this output should be 0, but there's some random noise due to this thing. Okay? So we normally calculate this noise in terms of its RMS value, square root of the mean of the square. And we know how to do that for coherent signals. Well, it's the same thing for a random signal. So what would we do? Well, again, this is voltage as a function of time. So we would look at that signal, we'll call it V out. V out of t for a certain amount of time. Well, it's square root RMS, square root of mean of square. So we would square it. So we'd square that signal. So now we have the signal itself had an average of 0, but the square certainly doesn't have an average of 0. We would look at it for a while. How long? As long as it takes, and we would average it. So square, there's the mean, and then actually we could just stop there, and that's the mean square voltage. Or we can take the square root of the whole thing, and that's a voltage in RMS. So we usually like to think of these random signals as their RMS voltage, because we can't predict anything about this signal. It's a completely random noise signal, and it's due to various random fluctuations in the components inside the op amp. Now you can have other sources of noise. You can have 60 hertz noise on your power supply bleeding onto this, or things like that. That's not what we're talking about here. We're not talking about those kind of coherent signals. We're talking about if you give yourself, power this with batteries, hang capacitors off the power supplies, make everything as quiet as possible, there are still noise, and simply put, that's due to random collisions of electrons inside the various resistors and transistors inside of here. So can't do anything about it. You cannot eliminate it. It is always there. So it's interesting to think about what does that RMS value mean, okay, in terms of this signal that we're seeing on the oscilloscope. And so I'm going to show you an old picture from an old book, but it's the best, simplest one I've ever seen. So this is an oscilloscope trace of a noisy signal. And you can see some interesting aspects of it. It occasionally stays bounded, but there's a finite chance that you can get just about anything out of that. Now, clearly, ultimately, this is power supply limited, but we're typically talking about signals that are 100 microvolts or less here. So, for all practical purposes, you can see there's a finite probability that a voltage spike of any particular amplitude can occur. And in fact, we assume that it's Gaussian, okay? So we assume that the distribution of voltage values is Gaussian. So obviously, most of the time, the output signal is going to be 0, and the probability that you get these really large spikes is relatively small. Or putting it another way, a relatively small percentage of the time will you see the voltage up here. And kind of a rule of thumb, and it's just a rule of thumb, but if you look at this sort of band of noise here, that's going to be about the standard deviation. So somewhere here in that bright band, that's about the standard deviation, or in other words, the RMS value of that. We can then define crest factor. And crest factor is simply how big is the instantaneous value compared to the RMS value. So let's suppose that this signal, you run it, you square it, you take the average of that squared value, and then you take the square root of that. And let's say that that comes out to be 1 millivolt. By a lot of standards, that's a very large amount of noise. It's a large amount of noise compared to what we're going to be measuring, actually. But suppose that the RMS value of that is a millivolt. So crest factor is simply what percentage of the time is it bigger than, so crest factor equals 1 means the signal is within the RMS value. Or put it another way, what percentage of the time does the crest factor, let's write that another way, what percentage of the time is the crest factor greater than 1? In other words, what percentage of the time is that voltage bigger than its RMS value, our hypothetical 1 millivolt? Well, if it's Gaussian, it's about 32%. So about a third of the time, that signal exceeds. Greater than 2 falls off pretty fast. And by the way, this is, any Gaussian variable behaves this way. How often is the variable more than 2 times the RMS value? 4.6%. And down it goes. Greater than 3. So again, if our op amp here has an output noise that is 1 millivolt RMS, really noisy op amp, how often is that output going to be above 3 millivolts? And the answer is 0.27%. In fact, and it goes on to 4 is 0.0063%. And in fact, we say greater than 6.6, almost never. So if you're running this signal into something that's nonlinear, where you're capturing these values and again, let's say we have a 1 millivolt RMS noise, the probability that that exceeds 6.6 millivolts is almost zero. So if you're trying to capture an event that exceeds 6.6 millivolts, you're going to have to wait a long, long time for that to occur. And so we assume that the noise is basically bounded within that. And keep in mind, that's plus or minus 6.6 of the RMS value. So that's how we treat noise. Other than these Gaussian statistics, and we're not justifying why we noise-based Gaussian statistics, we just say that it does at this point. Yeah?
So suppose a designer circuit such that the 6 millivolt is just on the upper edge of the ADC's acceptable range before it becomes damaged.
That's actually what I'm suggesting you do.
Okay. Because
Yeah.
it is possible for that signal to exceed that value and damage the ADC. Would you
Yeah.
still recommend
So
designing some sort of protection?
it will not damage the ADC. No. If you didn't hear the question, let me rephrase it and tell me if I don't. But your analog to digital converter will have some input range. So you're going to take, your noise source is going to have up to 1 millivolt on that. And so you can reasonably expect that that will never exceed 6.6 millivolts. So when you gain that signal up, let's say you gained it up by a factor of 1,000, 60 dB, well, then that would be plus or minus 6 volts, which certainly exceeds the input range of any reasonable A to D. So you want less gain than that. You want, so that a signal which is, think of it as this peak to peak amplitude of plus and minus 6.6 will still, after being gained up, will still fit in the input range of your AD. And do not, if you get something that's a little bit bigger, you won't blow the input protection on your AD converter.
What about things like transients, flood or not flood? Something from the
Oh, you can always blow things up in transients, yeah. The answer to that is yes. That's,
So my question is, do you recommend us designing a protection for the PC?
no. No. There are people that are really good at that, and they already put it on the chip. So I would leave it at that. I mean, the old days of putting Zener diodes everywhere as sort of input protection, we don't do that. Okay? Good questions, though. Okay, so that's how we treat our signal. And other than this Gaussianness of it, we don't really know anything about it. It's a totally random signal. We can't really much about what it's going to do 1 microsecond to the next. Right? It's just jumping around at random here. But the reality of that signal is that it is band limited, right? And certainly in the case of op-amps, if you did an FFT of this and analyzed its frequency components, you would see a 741 only has, when a 741 is set up as a unity gain amplifier, it has a bandwidth of, no, that's the other thing. No, the gain bandwidth product of a 741 is about a megahertz. So when you set the gain up to 1, the bandwidth's about a megahertz. So you would, the frequency dependent, this noise has, if we did an FFT, we wouldn't see any noise exceeding a megahertz, or it would be greatly attenuated out there. Okay, so that's physical noise, and you're actually going to be dealing with a dependent signal, a time-dependent signal like that going in. Now, we're setting your amplifier up with a higher gain, which means it has much lower bandwidth. You're going to want to gain, remember, this is your device under test. This is not your measuring circuit. This is what you hook to it. If we set this up with a gain of 100, so set it up as a sort of a non-inverting amplifier, like that. Resistor here. It's reasonable to ask, do the resistors add noise? Yeah, they do, but we can show that it won't be that much. If you set this up with a gain of 100, then it will have 1/100th the bandwidth, or only about 10 kilohertz. So with a gain of 100, obviously the noise is going to get bigger, right? But the bandwidth will get smaller, okay? So this is all, again, just the device under test. And we can swap that out for some other op-amp that's lower noise, or we can pull some tricks to get higher noise circuits, etc. Okay? But that's how we think of the noise in there. Now, how do we calculate it? Well, that's where we come up with power spectral density. And that was what those graphs that I showed you on the data sheet were earlier. So, the way we think of this 741 it's too complicated to think of all the different noise sources in here. We have a good theoretical understanding of that, and we've had a good theoretical understanding of the noise associated with transistors and such for my lifetime. Interestingly enough, one of the pioneers in doing those calculations, and if you look at any circuits book, the chapter on noise, go to the bibliography, and I guarantee you there will be multiple references to Alexander Neal, who was still living when I first came here. He was one of the pioneers in this area, and he did most of his work here. I believe he had 80 PhD students over the course of his career, which is unbelievable number of students over a 5-decade career. Anyway, so instead of thinking of the individual contributions of every little noise source and every little transistor, and if you want to learn a little bit about how complicated that is, take W4111 from me. But we just tend to think of it as a fictitious source applied to the input. Vn squared of F. A noise power spectral density, its units are volts squared per hertz. And now we think of this as noiseless. So think of a perfect amplifier with a little noise generator that somebody attached, a gremlin attached a noise generator. And that noise has a power spectral density. If you want to know the RMS value of a noise, so this is a power spectral density, and that gets to the root of why the units of this equivalent input noise, just like I said, equivalent input noise versus frequency from 100 hertz to 1,000 hertz. And forget for the moment that it kicked up here in the end. If you can't read that, that line is just below 25 nanovolt per root hertz. So we'll call it 25 nanovolt per hertz. So the power spectral density of this noise is 25, actually that's the square root of the power spectral density. So 25 by 10 to the minus 9 volts per square root hertz. Simply square that and you get 6.25 by 10 to the minus 16 volts squared per hertz. So all you have to do is square the values on this chart, and then you have the actual power spectral density. Now, since that's volts squared, we're running it through an amplifier with unity gain, which has a bandwidth of about a megahertz. So we take our 6.25 by